Ethan Buchman gave us a workshop, many of us, our heads were filled. New concepts are coming. Ethan, do you want to introduce yourself? Is there a microphone? Can you?
There is.
All right. Hi.
What's up?
I just say a few quick words before we start. First of all, thank you to Knock House for giving the space, and you know, encourage them by buying yourselves drinks. That would be great. This works, right? And so I'm Mike. I co-founded BlockSense with a few people here, Jim and Berto, who I think just left anyhow. And we're blockchain application developers, and we've worked with some of Tenderman's stuff, which Ethan designed, and I guess I'll pass it over to you so you can kind of introduce yourself and go from there.
Cool.
Thank you.
All right. Thanks for the stellar introduction, Mike.
Yeah, there's maybe three.
So, that's Mike. Round of applause for Mike. That's how you get an introduction. So I'm Ethan. I just spoke for about 6 hours straight, so my voice is a little bit strained, but I'm going to keep talking for you people. I have been working in the space for about 4 years now. I started in early 2013 when I bought my first Bitcoin. I was about to start a master's degree in computer science at the time, and I kind of fell down the Bitcoin blockchain rabbit hole and have yet to emerge. I'm slowly trying to claw my way out by getting into other things like, you know, organic farming and raising the chickens and stuff like this, but I keep getting pulled back down. So in 2014, when I heard about Ethereum for the first time, really early on, I kind of fell madly in love, and a huge part of my computer science education actually came through learning about Ethereum. That's when I first learned about like database tree structures and like serialization algorithms and like virtual machines and all this. And when I tell this to computer scientists, they're horrified for good reason, because there are many design flaws in the Ethereum stack, and having that be your first introduction to like many fundamental concepts in computer science is probably not the best way to start. But anyways, I ended up doing that master's, and it ended up mostly being on Tendermint because I was working for a company at the time called Eris, now known as Monax Industries, which was building an enterprise version of Ethereum, and we needed a better consensus algorithm, and we had heard about this Tendermint thing by this dude, Jay Kwan, in San Francisco, and so I ended up linking up with him in early 2015 and living with him for a few months, and he kind of mentored me, and I learned quite a bit, and have pretty much been working on Tendermint ever since. It was pretty much just two guys for a couple of years until early this year when we raised money and we started to grow, and now we're about 25 people and we're building the Internet of Blockchains together, and that's called Cosmos. So Tendermint is this general purpose blockchain engine that's useful for many different kinds of blockchain applications, and Cosmos is this public proof-of-stake cryptocurrency network that we're building on top of Tendermint that will facilitate interoperability and scalability across many different kinds of blockchains. I'll tell you more about that stuff a little bit later. Basically, we were at DevCon, Ethereum's DevCon, a couple weeks ago, and one of my teammates, his name's Sunny Agarwal, he's a young researcher in California who's doing a bunch of research for us on crypto economics and so on. He gave a really great presentation called Many Chains, Many Ecosystems that I failed to attend, but I believe Mike attended. And when I spoke with Mike about coming out here and doing my workshop today, he was like, yeah, it'd be great if you could also do the meetup and present Sunny's talk. So I was like, okay, you know, I'll do that. But I didn't really have a chance to review Sunny's talk very deeply, and like as great as Sunny is and as great as I know his talk was, I don't know it that well. I am going to deliver it to you, and it's got lots of great information about Cosmos and Tendermint. But before I do that, I'm going to do a talk that I prepared that I do know, that I also presented yesterday, called A Brief History of Distributed State. So I'll just launch right into it. So, distributed state, this is a fundamental problem. And this isn't just a problem for blockchain nerds and computer scientists. This goes like right to the heart of civilization itself and human societies, and has been a problem that we've had to address for thousands of years, right? This is the question of how do we maintain some kind of shared distributed state across a population so that we can all understand each other, have common values, and work together for whatever we're trying to build, right? And the fact that you can understand the language I'm speaking means that we share some kind of distributed state, right? There's a state machine in all of our heads that's replicated across all of us almost exactly consistently, because the words I'm using are totally unambiguous. You all understand them. And so that means that our language is one of these instances of distributed state, right? But there's much more. There's the tools we use to build our societies. There's the practices we have for raising children and organizing ourselves in civilization. And now we have democracy. We used to have kings and rulers and gods and all this stuff. And within a single society, we shared this kind of distributed state. And the fundamental challenge was, how do we replicate it onto the next generation? And how do we adequately update it in sync with everyone else without devolving into conflict and doing it in a way that actually makes sense with the rest of the world, right? So this is a fundamental problem that goes all the way back to the beginning of humankind and even to animals and other organisms. But you might call this problem the consensus problem. How do you keep a group of agents in sync with each other so that they can actually do something that's greater than the sum of their parts, right? And of course, the consensus problem is a fundamental problem in computer science as well. How do we keep a set of machines in sync with each other with some kind of consistent state, so that even if some of them fail, we can still have access to whatever service they're providing, right? And the same thing goes, this fault tolerance goes for humans as well. If there's only one person in your society that knows how to do something, and something befalls that person and they pass away, whatever it might be, then that skill is lost, right? So it's very critical that we replicate this information across many people in society. And so, in thinking about this problem quite a bit, and especially in thinking about some of the analogies between how humans have organized themselves and how humans solve the consensus problem, and things about leaders and assumptions about time and all this stuff, and about how digital networks do it, I realized that there's a really interesting fundamental analogy between the evolution of human societies over the past few thousand years and the evolution of digital networks over the past few decades. And what's even more interesting about that is I think they're coming to a head, and they're kind of colliding right now. And we're right at the forefront of that, and Cosmos is as well, and I'll get to how and why. So what I'm going to do is I'm going to take you through a brief history of distributed state on both sides of the spectrum, on the human side on the one hand, on the digital network side on the other, and we're going to walk through history as these things have evolved, see how they've kind of evolved in tandem in the same kind of way, and show how they're about to collide and what that's going to mean for the future of digital networks and for the future of civilization. So it's no small task. All right, so in the beginning, villages and city-states. So, when it all started out, we started in small villages. Everyone more or less knew each other. It was relatively self-sufficient, self-contained. You didn't have too much access to the outside world. You had very strong shared values that everyone kind of understood. You had councils that kept behavior in place, that punished bad behavior. There was shaming. There's all these religious traditions and so on, right? So very, very tight-knit communities where everyone kind of understood each other and were relatively self-sufficient. They grew their own food, or they hunted for their own food, or whatever. And at the same time, you also have city-states, which are a kind of more elaborate version of the village. You might have a wall around them, but still they're relatively self-sufficient, relatively consistent and shared values, relatively isolated from the outside world, right? And this is kind of like a paradisical environment, you might say, or that people might look back on romantically, because there was no, arguably there was no corruption, and everything was kind of like holistic. Obviously that wasn't actually the case. There was rampant corruption in many different societies, but work with me here. So in many cases there was some kind of ruler, or there was some kind of religious tradition that bound everyone. And I think a really interesting thing to understand about religion is that the word itself derives from the Latin religere, which means to bind. And religions really were the things that bound people together, that organized this distributed state across humans that were part of a single society, right? They all shared that same value system and had the same understanding of the world, and when something happened, they understood in the same way what that meant. Of course, nowadays, when as Nietzsche proclaimed, God is dead, and sort of the traditional institutions of religion have kind of been crumbling around us for the last 100 years. What is it that binds us together? Arguably, it's our network protocol. So there's potentially some kind of replacement thing happening where network protocols are emerging as the thing that actually bind us and hold us together and organize our civilization. And that's kind of where we're going to get to. But so this was this early state, self-sufficiency, little influence from outsiders, and so on. And so on the digital network side, you know, the village might be the single computer with a bunch of processes running on it, and the city-state might be like your little intranet, right? Relatively self-contained, self-sufficient, very little input from the outside. You have your own view and understanding of the world. Maybe you're running some encyclopedia or another. You don't really have access to the internet yet, whatever. And you know, this phase lasted for some amount of time. But then we move into the next phase, which is the age of empires. And so in the human reality, we end up in this world of somebody else's government, right? Alexander the Great moves in, or some other great dictator moves in with his massive army and just like conquers this huge geopolitical region. And suddenly that self-sovereignty that you used to have is now gone, right? And it's kind of a double-edged sword. On the one hand, all this stuff is going to be done for you, right? There's a military to protect you, there's all this infrastructure being built for you, all these other things are provided, maybe you don't have to work quite as hard, the quality of life might go up, you have access to all these other cultural innovations and so on, but at the same time, you've lost that self-sovereignty you had. You now have to pay taxes to Alexander, and you have to potentially, you know, follow his new rules. He was actually pretty good, and he allowed people to keep like their own cultures and religions to a significant extent, but others weren't nearly so permissible. But so there's that trade-off, right, between having everything provided for you on the one hand, and that being beneficial, and the tyrannical element on the other hand, right? So it's like the sort of two sides of the father, you might think, in sort of mythological terms, the tyrannical father and the good king, so to speak. So that's in the human realm. In the digital network realm, we have somebody else's computers instead of somebody else's government, right? And that's Jeff Bezos there, who is the benevolent dictator of Amazon, who is slowly conquering the whole world. I don't know if you've been paying attention, but he's literally taking over. In very much the same way Alexander did, benevolently, right? He's letting people maintain their own cultures and so on, but he's in control. He's the richest man in the world now, and his infrastructure is everywhere, and everyone's using it, and they more or less have to. I mean, there isn't really another option. And again, we have that same trade-off, right? Like before the Alexander, the king of AWS, came around, everyone had to run their own little data center, had their own server racks, right? And that's a huge startup cost. So the benefit here is, well, all this infrastructure is suddenly provided for you. Yes, you have to pay taxes to Jeff, and you know, yes, you're at his mercy because now he has complete access to your data, and he can shut you down if he doesn't like you and tell you to stop doing what you're doing. If you know you're gambling, running a gambling site in the U.S. or running a dark market or whatever it might be, right? But at the same time, he's providing this amazing service for you and doing all these things that now you don't have to worry about. So we have that same kind of trade-off, but ultimately, this kind of system isn't sufficient, right? People want that sovereignty back. They want more out of it. They want to be able to control their own data. They want to be able to put up the services themselves. They don't want to pay taxes. They don't want that censorship element. They want to take back control. And so we move into the next phase, which is the phase of sovereign nations. So in the damn it, I gave it away. So in the realm of humans, of course, we had the emergence of countries only a few hundred years ago. And before that, everything was pretty much an empire, right? But those empires were the geopolitical regions they governed were too large, it was too fragile, so they started to break down. And the underlying constituents started to demand and enforce their own independence and sovereignty. And so we have the emergence of nations with constitutions and the emergence of democracy as a way to coordinate, as rules of law and so on, as that new way to replicate state across people. It's like, okay, we have this constitution, everyone knows the constitution, we have this set of laws, everyone knows the set of laws, this is what governs our society and what everyone agrees on, this is what the consensus is, right? And so, you know, this is great because now we have this like national independence, some of that sovereignty is back, some of these guys have their own currencies, in fact many of us have our own currencies, and we have our own rules that kind of evolve according to our own traditions, we can pick which language we want to speak, and so on. In most countries we have, you know, a couple of languages, etc. But at the same time, these are still very large geopolitical regions, and as we're starting to see after a few hundred years of this sovereign nation experiment, it's starting to break down. Once again, the same problems that plagued the empires are now plaguing the sovereign nations, because the federal institutions that govern the thing, that have kind of replaced the old dictators, are still relatively impervious to feedback, right? That maybe we vote once every 4 years, but what difference does it really make, right? It's like that South Park episode. You're voting between a douchebag and a turd sandwich, right? It's the same fucking thing. One might be on the left, one might be on the right, but fundamentally, like, nothing's really changing. Of course, in the U.S., it's much worse. Arguably, something has changed. We have like an absolute buffoon in charge, and we're pretty much the pinnacle of the collapse of this paradigm, of this era, right? It's like the constituency is so fundamentally polarized that they can't agree on anything, that they're practically at war with each other. And there's a real chance that civil war is going to break out between, you know, these two factions. So as much as this experiment was relatively successful and brought us, you know, the whole digital age in the first place, it's kind of breaking down now because the structure in place to govern is too fragile given the pace of information. The exact same thing that happened to the empires, right? They couldn't hold it together because the cultural adaptation in each location was moving too fast with, you know, the advent of, say, originally roads to distribute information and then the printing press and whatever. It just broke the whole thing down. And that's happening again with the internet, right? The internet demolishes these artificial borders that we've set up. And so what does it mean to have a nation state in the face of the internet where people are now global citizens, right? It's a real problem. So, okay, so what does this look like in the digital network realm? Well, the same thing is happening to Jeff Bezos and to Mark Zuckerberg and to the Google crew and so on, that their hegemony is being challenged. People are saying, you know what, forget these guys. We can run our own networks on our own machines in a peer-to-peer fashion, right? We can run our own digitally sovereign, independent networks that we control, that can't be censored, that can't be shut down, where we don't have to pay fees to some dictator, right? That are completely peer-to-peer and open source. And so we have things like Bitcoin and Ethereum and Monero and Dogecoin even and Zcash. Dogecoin is really like a truly amazing example of this because it's like, it's emblematic of the capacity for humans to come together over ridiculous cultural means, right? And like many. No, but it really is a resurgence of like an ancient religious phenomenon, right? Like if you look back with your modern perspective on many of the ancient religions, it's like they're ridiculous, right? Like they're absurd. There's no other way to describe it. Like what are these people doing? But under the hood, if you kind of peel it back and think about what's going on, there's a cultural binding that's happening there that despite the ridiculous manifestation, there's something important underneath. And to discount that is to kind of miss the nature of humans and cultures and like collective organization itself, right? And so the emergence of Dogecoin really kind of re-emphasized that it's still there within us and that we're really longing for that connectivity, for those binding forces. And Dogecoin is really, in a sense, a religion, right? And it sent the Jamaican bobsled team back to the Olympics, and it funded all kinds of ridiculous stuff. And now there's Popcoin that's funding Dennis Rodman to go meet with the leader of North Korea, right? Like the sovereignty of these networks is really, really, truly amazing. So that's incredibly powerful. And in the same way that the nation states kind of tore down the previous empires and the previous dictators, benevolent or not, these digital networks are now going after the somebody else's computer empire, right? They're going after the social networks and the payment processors and so on. But we have the same kinds of problems, right? The underlying constituencies for these networks are too large and too diverse for them to be governed by a single protocol that's relatively impervious to the feedback, right? I mean, look at what's happening in Bitcoin. The community is totally divided in at least two, if not more, factions, and it's blowing up, right? So they're splitting and they're forking, and it's causing all kinds of trouble and strife and conflict. So, and the same thing is probably going to befall some of the other communities. I mean, Ethereum split before; it might split again, right? There's all kinds of changes that are anticipated to happen. Some of the other communities have held it together a little better, but the point is that these networks don't scale to as they currently are. They can't keep up with the complexity of their underlying citizenship, so to speak, right? And so we need something better. And what does that look like? Well, let's move on to the next phase. So it's almost like we're going back to villages and city-states. There's something of an archaic revival. And it kind of made sense initially. And when we started in villages, there was no other way to start because we had small bands of humans that came together, slightly larger sets of kin and whatever. And that grew until it became empires. And once we became empires, it was so big that it became fragile and it started to break down. And now we're shrinking back, right? So we went down to nation states, and now it's as if we're going back to villages and city states. except it's more like eco-villages and metropolises, right? And so we almost had to go through this empire stage to get back to the initial stage, and we learned so much, and we built all this technology and civilized mechanisms, and now we're retreating back. I don't want to say retreating, but we're engaging this sort of archaic revival where people are much more conscious of the local community. People are buying local. They're taking up urban farming. Like young people are going back to the farms. Everyone is concerned with like their impact on the environment and so on. And people are starting to identify much more with their cities than they are with their countries or these larger geopolitical jurisdictions, right? And for the first time in history, more than half of the world's population lives in cities. Cities are really the center of it all. Many Montrealers they love Montreal, and the Torontonians, they love Toronto and they fight to the death over it. And who cares about Canada? Like, great, Canada's cool and all, but your passion is really with your city because that's where you live and that's where your communities are and your engagements are and so on. So there's this huge like archaic revival back to these original principles of local jurisdictions and self-sovereignty that the nation state doesn't really matter as much. And that makes a lot of sense because these local jurisdictions can be much more responsive to local feedback, right? Like if you need a single federal government to govern Montreal and Toronto and Vancouver and Calgary and Edmonton and so on, and all across the board, all of these cities are going to have very different needs and requirements and cultures and whatever, and to try to govern them all with a single federal jurisdiction, it's not going to work as the pace of life continues to accelerate with our technology, right? So from a fundamental like information theoretical perspective, it's going to break down the same way the empires broke down, and it's happening. And the cities are starting to step up, and people are talking about like global parliaments of mayors and this kind of thing, right? So this is a really fascinating problem for people to think about, is how to reconceptualize the world economy and the world political realm in terms of city-states instead of nation-states. And I think we all kind of anticipate that that's coming, but no one really knows how to think about it because many of us feel that the nation-state has provided so much of the context for the last few hundred years for understanding how to coordinate with each other that we don't really know what would come next, right? But if you think about it, like, that's not really that true. I mean, we do have these common sets of laws that make it easy. You go to Montreal, you go to Toronto, you have the same body of law, but like, I'm in Montreal and I can't turn right on a red light. Like, what am I supposed to do about that? So there, really, it throws me off every single time, right? So there are obviously fundamental distinctions between our cultures. Sorry. Anyways, you know what I'm saying. So, of course, two of the really big things that we don't really know how to solve when it comes down to reducing the power down to the municipality from the federal level is defense and currency, right? So defense, I don't know how to solve. Like, who gets the nukes when America breaks up into pieces? That's a really tough question, and I don't really have an answer, but I'm going to keep thinking about it. On the currency front, though, I think there's a lot of interesting stuff we can do. So if you look at the euro, the euro is falling apart, and I have bets with a number of my teammates that the euro will no longer be the dominant currency in half of the countries it currently is within 4.5 years. So I think I'm doing pretty good so far. Anyone else want in on this? Yeah. So this is in the human realm. So what about the digital network realm? Well, this is where Cosmos comes in, and the idea of an internet of blockchains or a network of community currencies, and breaking down these larger sovereign networks like Bitcoin and Ethereum into underlying constituent parts that are more in tune with their community. And I think a huge part of this is going to actually be basing those networks in local jurisdictions so that they can be responsive to local needs and so that they can actually scale, because so much of your daily commerce and your daily information exchange happens locally, right? You go to work locally. I mean, sure, people have remote jobs, but at the end of the day, you have to eat, and that food has to get to your body, which is here right now, so it has to travel through your city one way or another. And obviously, it would be far superior if it was grown closer to you, because then you're incurring less overhead to actually continue to sustain yourself. So in the same way, these digital networks can and probably should be, in order to scale, much more locally based, right? I mean, it's totally insane that when we're all looking at the same image, every single one of our computers has to communicate with California before we can see that image, right? Like, it's nuts. So, arguably, the solution to the scalability problem in these blockchain networks is to break them down, to shard them, so to speak, into many more independent and sovereign networks that care less of, they're more like intranets with respect to their municipality, but they still maintain tight bonds and tight, say, trade agreements, you could say, with many other municipalities around the world. So the idea behind Cosmos, at least initially, is to start this experiment on a global scale with different cultural communities, right, and different virtual machine communities, I guess you could say, different approaches to designing cryptocurrencies. But ultimately, I think the long-term vision, at least for me, is to bring this down to a local scale and to actually derive the global scalability of blockchain networks from basing them in local jurisdictions that cater to the needs of those local individuals. And I think by doing that, we have a much better shot at scaling than we do with these crazy, globally decentralized, anonymous sets. Partially because you have a much larger chance of getting accountability at a local level, right? Whereas when you have all these validators spread out over the world, and many of them are decentralized, and you don't know what they're up to, it's a lot harder to actually hold them accountable with like the things people care about. I mean, sure, you could slash their stake or whatever economically, but there's a lot more to human experience than just economics, right? There's all the culture and political elements and people actually coordinating together. So that's kind of the vision of Cosmos, is then to build these modular tools that initially we're going to put up as this first instance of the Cosmos network that's going to enable many different kinds of blockchains to interoperate with each other, but which ultimately can be used by local communities to build networks that run their fundamental civilized processes in the way that suits them, and with the technology that suits them, and with the technology that was built by their own people that solves their specific needs and that is in tune with their various processes and culture and so on. So that's the idea behind Cosmos, and I think that's the proper approach to actually scaling these networks, and that this is how these two threads of human distributed state and digital distributed state are actually going to combine in the very near future and solve all the world's problems.
Yay. If you want to learn more, these are our websites,
And that's it. Cool. Questions? Should I go on to the next one? I got this
That's a team effort.
Yeah.
Is it?
Yeah.
Nero is the one who carried that.
No, I think it's just I feel like
Okay, so
something along the lines of
so that was my talk. This is Sunny's talk. Many chains, many tokens, one ecosystem. I'm going to give this a go. Who am I? I'm not Sunny, but this is Sunny. Sunny is a researcher with Tendermint with particular interest in proof of stake and blockchain interoperability. How many of you know what proof of stake is?
Yeah.
Cool, pretty much everyone. We'll talk about it a little bit. He is the co-founder of Blockchain at Berkeley, which is the blockchain program at University of California, Berkeley. He previously worked at Consensus, which is basically the largest blockchain company. They're mostly based out of Brooklyn, but they just opened an office in London, and they build all kinds of stuff in the Ethereum ecosystem. Sunny also teaches a class on Switzerland at Berkeley. I don't know how he managed that, but it's pretty awesome. Switzerland is really cool because Switzerland pretty much nailed it as far as decentralization. I mean, it probably helped that they're surrounded by mountains and all super rich, but it's definitely an example that I hope the rest of us can follow. So maybe I should take Sunny's class. Anyways, that's Sunny. I'm Ethan. We recently hired Sunny because he's brilliant. And he put together this talk, and Mike asked me to present it, and so I'm excited to do so, and hopefully I live up to Sunny's standards. Oops. Okay, so this is a talk more specifically about Tendermint and Cosmos, and kind of how it all works at a little bit more technical level and what the ecosystem looks like and why we've designed it the way we have. I mean, yeah. Okay, so most blockchain stacks look something like this. You have this like simplified monolithic architecture. At the very bottom, you have your networking, which is like your peer-to-peer networking layer. Then on top of that, you have some kind of consensus algorithm, which is what enables all the different peers to stay in sync with one another. And then finally, you have your application state, right? And that application could be anything you want. It could be the Bitcoin application state, which is a bunch of weird, funky transactions. Could be the Ethereum application state, which is this really weird virtual machine that lets you write arbitrary smart contracts programs that will most likely make you lose money. And then there's many other kinds. There's different kind of application states that are a little more safe than Ethereum. There's different kind of cryptocurrencies, whatever. But the problem is, pretty much universally, they have this monolithic approach. It's almost like blockchain engineers forgot about good software engineering principles, and they just kind of like threw everything in a bucket and figured it was too complicated for anyone to use anyway, so it didn't matter if they used good software engineering. But so this is what we're kind of stuck with. So Ethereum did the same thing. They built this monolithic stack where their application is this virtual machine, the Ethereum virtual machine, which is pretty cool because they provide a full-blown virtual machine for you to write applications in, or what people call applications, decentralized applications, dumb name, but whatever. And so these dApps are basically like little scripts. People call them smart contracts. They're programs written in Ethereum's programming language that run on the Ethereum virtual machine. So you deploy one of these contracts, one of these programs, the whole network sees it, they all store it, and then anytime someone sends a transaction to that contract, it'll execute that code, right? So you can run some kind of business logic, or you can have complicated escrow or joint accounts, or do whatever you want, really, right? And that's pretty cool. It enables like all kinds of additional functionality beyond what Bitcoin can do. It's also nice because the different dApps can communicate with one another. So if you know that there's another contract running in the Ethereum world that has some functionality that you want to take advantage of, your contract can call that contract and ask it for some information or to do some processing on its behalf. And so there's kind of this like interoperability built in, but only if you're an Ethereum smart contract. If you're not an Ethereum smart contract, well, good luck getting anything out of the Ethereum blockchain, because all the serialization protocols and everything was kind of invented from scratch, and there's a lot of weird things to understand. So Tendermint took a little bit of a different approach. Tendermint decided that we would at least partially go back to good software engineering practices and insert an interface between the consensus and the application. Arguably, we could do the same thing down here, but we haven't had the need yet. But we did have the need between the consensus and the application. And let me tell you why. So before the last year or so, I had spent a lot of time working with the Ethereum codebase. Because when I started working for Eris Industries, now Monax, my job essentially was to take the existing Ethereum codebase and make it work in a more general enterprise setting. And so we hacked all kinds of things in that ended up all pretty much being bad ideas at the time. But it was very difficult to work with, and we had to maintain a fork of the software, which meant we had to have a copy of the entire code base, and whenever it was updated upstream, we had to figure out how to pull in those updates. So it was this big, complicated process. What was even worse was we wanted to replace their consensus algorithm, because they were using proof of work, and proof of work didn't make any sense in an enterprise setting. It was just wasteful and slow and insecure, ultimately, in that kind of setting. So we needed to replace it with something more consistent. So eventually we discovered Tendermint. And at the time, we were like, okay, how can we combine? Tendermint was also written in Go. Ethereum was written in Go. So we thought, how could we combine these two things together? And we couldn't find a good way to do it. So we ended up just implementing the Ethereum state machine from scratch on top of Tendermint. So Tendermint, which had initially been this like this new consensus algorithm plus a cryptocurrency, proof of stake based cryptocurrency, now was about to get this virtual machine addition, right? And so we did it. We implemented a fully compatible Ethereum virtual machine that's now what is known as Hyperledger Burrow. So it eventually got accepted into the Hyperledger project. But the problem we were having at the time was like, well, what if someone doesn't want a virtual machine? Or what if they want a different virtual machine? Or what if they want different functionality or different cryptography and so on? Are they really going to have to, we had these instructions on what to do, and it was basically like fork the code base and then make all the changes and then, be willing to maintain that indefinitely and pull in all our changes if we refactor the whole thing. And like, that sucks. That's not a good thing to have to read or to have to follow. So eventually, later that year, this was like late 2015, Jay, the co-founder of Tendermint, or really the technical founder, came up with this brilliant idea, which was that why don't we separate the consensus engine from the application state? And by doing so, we can have arbitrary applications written in any programming language we want. Forget about the Ethereum virtual machine and its crappy languages like Solidity. We can use languages that have existed for 30 years that everyone is comfortable with, that have real debugging and execution environments like Java and C++. Not that those are very good languages, but a lot of people are comfortable with them, right? But there's other things like Python and Haskell and other functional languages, whatever. So this was a really exciting idea. He went and implemented the thing, and then almost right away, we had a working project where now we have the consensus engine running in one process and the application running in a separate process, and they communicate over a socket, right? And they're just passing messages back and forth over that socket, and that allows us to build the application in any programming language we want. And so today we have applications running on Tendermint that are written in Java, C++, C, Haskell, OCaml, Erlang, Python, JavaScript, Go, and so on. And it's easy to add more languages. All you have to do is implement this interface we've defined, this ABCI interface, and it just simply communicates over a socket, standard computer science stuff. So, a few notes about Tendermint consensus then. So, consensus is an old science. It goes back to the late 1970s, basically around the time that people decided they wanted to use microprocessors to run airplanes. This was kind of a genius idea. It was like, okay, we can run these we have these little computer things, why don't we use them to help manage the airplane flight? It'll reduce the incidence of crashes, and it'll make it more manageable and more precise and exact and so on. Like, that's great. The problem was they needed fault tolerance, right? So they needed multiple microprocessors on a single airplane that were all connected and that could stay in sync, right? So they had this consensus problem. How do we keep those microprocessors in sync? But they had it even worse than that, because an airplane at 30,000 feet in the air is in a highly adversarial environment. It's impacted by all this solar radiation and all kinds of bombardment by other particles that could cause non-deterministic behavior in these microprocessors. It could cause bits to randomly flip or operations not to execute the way they're anticipated. So even though they can get extremely precise network connections between these processors, right? They have like wires that connect them directly so that the message latency is incredibly low, like on the order of microseconds or milliseconds or whatever. They can't solve this adversarial problem that the environment can cause non-deterministic behavior. So they formulated, Leslie Lamport was one of the guys who was in charge of figuring this out. He formulated this as the so-called Byzantine generals problem. And the reason he called it the Byzantine generals was because he really likes to confuse people with references to ancient Greece. And so he came up with this analogy where it was like, okay, you have a bunch of Byzantine generals and they're going to attack Rome, right? And so the problem is that one of those generals might be a traitor, right? And so how do these generals, who are distributed around Rome, who can only communicate by a messenger, agree on a time to attack Rome when one of them might be a traitor? And he found some very interesting results that in certain cases it was actually impossible, and depending on what kinds of assumptions you make, it may or may not be possible, and so on. And so he spawned this whole field of consensus science, starting with this Byzantine generals problem. And so it wasn't until the late 1980s that a real useful solution to this problem came out. It was called the DLS algorithm, named after the authors Dwork, and Stockmeyer. And even still, it wasn't good enough to be used in industry. Then, in the early 90s, Leslie Lamport struck again when he came up with the Paxos consensus protocol. Paxos solved the problem in the absence of Byzantine behavior. So this word Byzantine came to mean any kind of arbitrary or malicious behavior within a system, right? And so on an airplane, you actually need that. And he was able to solve the problem in the kinds of networks you have on an airplane, where they're very high reliability, like extremely high reliability. But on the internet or on more generalized networks where you don't have that kind of reliability, it's a very, very difficult problem to solve. And so he kind of focused his attention on solving that problem when you don't have Byzantine behavior, when you don't have this kind of arbitrary malicious behavior where the only kind of failures you have are machines crash, right? And so he came up with an algorithm called Paxos. Why? Why did he call it Paxos? Because once again, he wanted to confuse everyone with references to ancient Greek literature or Greek cities. Paxos was like some ancient Greek city-state where they had some clever way to do their governance, where like everyone kept a little book of records of all the decisions, and if like someone wasn't around, someone else had the record, and it was very confusing. So this is what happened with Paxos. He came up with it in the 90s, and he tried to get it published, and none of the journals would publish it. They all refused because it was too confusing and they couldn't understand it. In about 95, one of his buddies wrote a paper called like Paxos Explained, where he tried to explain better than Leslie possibly could how Paxos works. It wasn't until 1999 that the protocol finally got published, because finally people could get a handle on how it actually worked. That said, it's still incredibly confusing to this day. It's so confusing, in fact, that almost no one knows how it works, no one can explain it, and it's riddled with black magic. So any real implementation of Paxos requires like this voodoo magic from weird engineers that just kind of like wiggle their fingers over their computers. I'm not even kidding. It's so bad that in 2013, it spawned a research effort at Stanford by a graduate student there to build a new consensus algorithm, starting from first principles, whose fundamental concern was that it would be understandable. So this is how we decided to design it, not from any other security concern or anything. He's like, I'm going to design a consensus algorithm that first-year university students can understand. And he wrote his thesis on it, and he even did an experiment where he presented Paxos to the first-year students, and he presented his new algorithm called Raft, and proved that they could understand it. So anyways, now we have Raft, and Raft is understandable and it's great, but it still has all kinds of problems. But I went totally off tangent because I love that story. Hope you don't mind. Getting back on track. This Byzantine fault tolerance problem. So Leslie had turned his attention to the normal consensus problem, but in late '99, this other protocol came out called practical Byzantine fault tolerance, because they claimed they finally solved the Byzantine fault tolerance problem in unreliable networks in a practical sense. And everyone was kind of like, that's amazing, but no one actually cared to use it. Why did no one care to use it? Because everyone was very trusting, right? So no one cared to actually run a consensus algorithm or a replicated database with other people that they didn't really trust, which is kind of a reasonable thing to do, right? Like if you're Google, you're just going to run your database across other Google servers that are managed by Google employees that have legal contracts with your company, so that if they mess around, you just sue them or send them to jail or whatever, right? So you use the legal system, you don't have to use computer science. And so that's kind of been the standard. But then in 2009, everything changed because Bitcoin showed up, right? And Bitcoin had a brand new approach to the problem that drew on none of the previous literature, didn't mention consensus at all in the paper or reference anything relevant. And it took a few years before people really started to figure out that, wait a minute, this is the consensus problem all over again. But now it's happening in unreliable network on a global scale with economically incentivized actors, right? And this was a total breakthrough when people started to understand what was going on here. And it really brought them back to the science of Byzantine fault tolerance and try to understand what Bitcoin introduced in that context and what this blockchain thing is in the context of the 40 years of consensus research that came before it. And so I feel I have a better understanding of what that is now. To me, a blockchain is just a data structure that is an optimization in the design space of Byzantine fault tolerant consensus protocols. And the first person that really figured that out was my co-founder, Jay Kwan, who in 2014 was the first person to go back and say, okay, we can use these old Byzantine fault tolerant protocols. Either he started with DLS, which was the one from 1988, and he took that and combined it with the blockchain data structure to produce Tendermint. And he said, here is a blockchain-based Byzantine fault-tolerant consensus engine that's practical, that can support thousands of transactions per second, on top of which we can build cryptocurrencies that are much more energy efficient than Bitcoin. That was one of his driving motivations, was the energy efficiency of proof of work and of Bitcoin. And so that's how the project pretty much began and has been evolving ever since. The consensus algorithm has evolved considerably and is much better than it was then. And we're happy to report that now it's pretty much the state-of-the-art, leading Byzantine fault-tolerant implementation on the planet. So, back to Sunny's slide. I'm sorry, Sunny. This idea of a consistent proof-of-stake PFD consensus algorithm. So proof-of-stake had kind of been around for a few years, but in general, it wasn't secure. And the problem with proof-of-stake is that there's, as people say, in proof-of-stake, there's nothing at stake. Which is to say, in proof-of-work, the thing that prevents you from forking the chain infinitely is that you have to actually consume resources to do so, right? And so there's a huge opportunity cost to being malicious. In proof-of-stake, where instead of having to burn external resources, your ability to participate is based on your stake in the network, there's kind of nothing holding you back from forking the blockchain infinitely and from trying to double spend all over the place. And so in early 2014, Vitalik, the founder of Ethereum, invented this idea of Slasher, which was a proof of stake where to participate, you had to create a security deposit. You had to bond your stake into a security deposit that could be destroyed if evidence was published of your misbehavior. And so Tendermint was the first to implement this in such a way that it was highly consistent and immediately, instantly finalized. So unlike Bitcoin, where you have to wait some number of confirmations before you can feel secure about the validity of your transaction, and the same with many other blockchains, Tendermint said, no, we're going to have instant finality. And the reason it was able to do that was because it was drawing on classic academic work in the field that always provided instant finality, because that's what everyone wanted, right? So that's how Tendermint ultimately combined these old school BFT consensus algorithms with the new school proof of stake ideas to provide this consistent kind of instant finality blockchain that became so popular now. So, of course, it can be used for public and private chains. We haven't seen it been used for public chains yet, but we will with Cosmos, so that's coming up around the corner. Instant finality, we've mentioned, highly scalable. So this is a contentious point. Some people will look at it and say, it's not scalable at all, because there's a limit on how many people can actually participate in the consensus. But Tendermint is designed in such a way that it supports very efficient light client proofs, which means you can get almost the exact same security as running a full node by only verifying a small amount of data. And what that lets us do is stitch together many different blockchains that can all verify the state of each other without verifying everything. And so using that, we can scale, and we'll get into how that works a little bit more. Finally, Tendermint has served as the basis for other proof-of-stake systems like Casper. So Casper, which is Ethereum's proposed proof-of-stake algorithm, actually had found its roots in Tendermint, but was a little bit frustrated with some of the constraints of Tendermint, and much of the work in Casper has been around trying to relieve those constraints, potentially at the expense of efficiency and of this instant finality. So I'll talk about this point right here. Guarantees safety in asynchronous and liveness in weakly synchronous environments. You all understand what that means, right? No. So I failed to mention in my little expose on the history of consensus that fundamentally there are two things we're concerned about in consensus algorithms. And I think these are actually a lot more general than just consensus algorithms, but we call them safety and liveness. Safety is the idea that nothing bad will happen, and liveness is the idea that eventually something good will happen, right? And I think these are concepts that apply in many aspects of our life. Where it could be that if you think about a business deal, right? When you have a business deal, you want the legal system to be structured such that you can make progress. So eventually something good will happen. You'll be able to actually get to a deal because you have some common set of rules and laws that you can count on. And you want it to be structured that nothing bad will happen, so that there's punishments and incentives in place to make sure you actually coordinate. So in consensus systems, we have the same thing. We want to have safety, which ultimately means that no two nodes will ever disagree. Everything is always consistent. And we want to have liveness, which is to say eventually everyone will agree on some value. Everyone will agree on the same thing, right? Now it turns out it's impossible to get both of these things with a deterministic protocol in an asynchronous network. So in 1985, this paper came out by Fisher, Lynch, and Patterson called the FLP impossibility result, named after them, Fisher, Lynch, and Patterson, which basically proved formally that you cannot have both safety and liveness with a deterministic protocol in an asynchronous network. What does asynchronous mean? It means there's no upper bound on the message latency. Ultimately, it's an unreliable network. So this kind of threw everyone for a loop, and it's like, oh, well, consensus is impossible, we should all give up. But no, there's all kinds of ways to get around it. Either you introduce non-determinism, or you introduce some kind of synchrony, i.e. some kind of assumption about time. And so most of the protocols that we look at or that we're familiar with operate in this weak synchrony condition, where we have the minimal assumption about time necessary to get around the FLP result. And so Tendermint is one of these protocols that guarantees safety in an asynchronous environment. So it means regardless of the upper bound on message latency, even if it's infinite, we're never going to disagree. But we can only have liveness if we have some kind of synchrony. Bitcoin's very different. Bitcoin doesn't give a shit about synchrony. Bitcoin will fork. It forks every day, right? I mean, anyone can mine a block as long as they have hashing power, right? And eventually they will. So from Bitcoin's perspective, it's not safe at all in an asynchronous network. Bitcoin makes a very strong synchrony assumption, which is that people will hear about blocks very quickly. And if they don't, it will fork infinitely. So it's easy to prove that Bitcoin is not safe in an asynchronous environment. Arguably, for some people, this is okay. Now, Casper, the Ethereum team, they're currently using proof of work, which again, not safe in an asynchronous environment, but they would like it to be. So they've been developing Casper kind of starting from Tendermint to also be safe in asynchronous environments and live, but it's a lot more, it's I think a little bit more difficult to understand. Actually, very recently they made significant simplifications, which are kind of impressive, but they have given up the instant finality aspect. So it takes a lot longer to get confirmations about your transactions than it does in, say, Tendermint. And if that's something you want, if you want to know immediately that your transaction is valid, then Casper's not going to do it for you, Tendermint will. So there is a little bit of a coopetition between the two teams, but they kind of complement each other, and I think they'll be useful in different kinds of circumstances. All right, Sonny, how am I doing? So, thanks. I've never seen him give this talk, so I have no idea how to get it. There are going to be slides where I just don't know what to say. So this is Bitcoin. We talked about this a bit. Basically, blocks are produced roughly every 10 minutes, but because Bitcoin is allowed to fork, because it's not asynchronously safe, we have to wait quite some time before we can consider a block confirmed, right? So only after it's buried beneath, say, 6 blocks do we consider, okay, now the probability of this thing being reverted is sufficiently high for me to trust it. But there are certain circumstances when there's network contention, or when there's been a bug identified in software, that you have to wait much longer, or that the developers recommend that you wait much longer because it's unclear how things are going to shape out. Yeah.
You said it always forks. I think what you mean is, just in case someone's misunderstanding, it's not a permanent fork. It's a fork that collapses after one block or two.
That's exactly right. So you have this one block that got mined that is eventually going to be forgotten because some other chain got longer, and that's a natural part of the Bitcoin blockchain's evolution, essentially, and about many blockchains' evolution. But Tendermint will never do something like that. Tendermint will never have competing blocks at the same height, unless its assumptions about the number of faulty nodes have been violated, right? And then the system kind of collapses catastrophically. But one of the nice things about Tendermint is that you can hold to account the people that violated these guarantees. So anyone who was malicious can be identified, so you know exactly who committed the fraud, so to speak, and so you can reboot without them. But that reboot process has to happen from an external protocol that's defined at a social consensus level rather than at a technical level. And that's a little bit of a problem, but we're working on trying to solve that as best we can. So unlike Bitcoin, which takes those 10 minutes, Tendermint, this is the Tendermint logo, the all-seeing eye, takes roughly a few seconds with hundreds of validators spread across the world, and only ever makes one block at a time, and is constantly moving forward. So that was a bit about Tendermint consensus. I think now, if I'm not mistaken, we will be talking about the applications. Yes. No. So, for instance, what can you build on top of Tendermint? Well, you can take, and this is what we did. Now that we have this ABCI thing is amazing, right? Because we have this Tendermint consensus engine, super general purpose, doesn't give a hoot what's in a transaction. A transaction, as far as Tendermint is concerned, is just arbitrary bytes. An arbitrary byte array with no semantic meaning. Tendermint doesn't know anything about it. It's completely up to the application what that transaction means. right? And if it's valid. So when Tendermint receives a transaction, it has no idea if it's valid, and it doesn't even know how to interpret it. It must forward that transaction to the application. The application can let it know, is this valid or not, right? So you can build whatever you want in that application, including Ethereum itself. And of course, we did that with Eris, with now Monax. The Hyperledger Burrow is basically a re-implementation of Ethereum from scratch as an ABCI application on top of Tendermint. But we can do one better. We can take the existing Ethereum code, the Go Ethereum code base that is running on the live Ethereum network today, that's been well audited and so on, and use that as a library to build our application. And that's exactly what we've done. We call it Ethermint, where we're taking the existing code base, we've made almost no changes to it, and we're running it as an ABCI application on top of Tendermint, which is an incredibly powerful thing to be able to do, both from the perspective of interoperability between different blockchains and from, say, the perspective of enterprise adoption. Because to go up to these enterprises and tell them all of a sudden they have to program their smart contracts in some obscure language that has almost no debugging or error checking support, i.e. Solidity, is kind of a hard sell. But if they can take their existing code bases that they've been working with for decades, that they have debugging and error checking support for, and with relatively few modifications, suddenly plug them into a distributed consensus engine, well, that's kind of amazing. So that's what the ABCI protocol or interface enables folks to do, and that's what we've already done with Go Ethereum. So now what we're doing is we're building a general purpose software development kit, or SDK, for building applications in Golang on top of Tendermint. So ABCI apps in Golang. Now, of course, you can build your apps in any programming language you want, and like I mentioned earlier, there are members of our community building them in many different languages. Because we're building the Cosmos application in Go, instead of just assembling it all together into the final application state, we're stepping back and trying to take a more modular approach to build this framework, this SDK ultimately, that will be a general purpose way for people to build applications in Go that run on Tendermint. And so the way the SDK works is, instead of like a general purpose Turing complete Ethereum virtual machine on which you program these weird smart contracts, the SDK is going to be a much more constrained framework in which you have many different kinds of plugins. And the plugins provide the different functionality you might need for your cryptocurrency or for whatever application you might want to build. And so you can have different kinds of cryptography in there for checking different kinds of signatures. You can have a coin plugin for having some kind of coin or a multi-asset coin. You could have a voting plugin, you could have a governance plugin, there's going to be a staking plugin for doing proof of stake, and so on. So the idea is to build this general purpose framework for writing applications in Go that we could then use to wrap the Go Ethereum libraries and provide Go Ethereum again as an ABCI app, but within this framework. And the reason we want to do that is because one of the other plugins is going to facilitate inter-blockchain communication. Oh, I nailed it. So, IBC, inter-blockchain communication. So, one of the plugins in the Cosmos SDK is this IBC module that allows different blockchains to understand each other. And the way that works is using what we call a light client protocol. So, as I mentioned earlier, a light client protocol allows you to get the same security out of a blockchain without verifying the entire set of transactions, right? And so, the way that actually works is, in proof of work, basically, there's a light client protocol that's known as SPV, Simplified Payment Verification. But because proof of work requires verification of all the work done all throughout history, those light clients still have to validate all the headers from all the way back, the entire history. And they have to verify the proof of work, and then once they verify the proof of work, they can do some simple light client proof called a Merkle proof on the latest state to know that they're up to date. In proof of stake land, you don't have to verify the whole history. All you have to do are verify changes to the validator set, which will happen much less frequently than every single block, right? And if the validator set only changes a little bit, and you know most of the validators already, you can jump ahead quite a bit. So the light client proofs in general in proof of stake land are much more efficient, and Tendermint has taken taken on particular pains to make sure that light client proofs remain efficient. There are a number of other proof of stake protocols out there that, they have interesting cryptographic properties or whatever, but they're not quite as efficient in the light client manner. So the light client efficiency is super important, not just for light clients, like for mobile wallets or whatever, but you can also have blockchains be light clients of each other, right? So this is where things get really interesting. So now, see, the problem before with scalability is that everyone has to process every transaction, right? It's never going to work. So if you want to break this thing up into multiple blockchains, they have to be able to verify the state of one another. And by having efficient light client proofs, you can do that easily by programming the light client into the blockchain. And the protocol that we've built around that is what we call IBC, the Inter-Blockchain Communication Protocol, which is effectively just a light client protocol that's built into the blockchain application. And so that is going to be a plugin within the Cosmos SDK that will allow anyone who's building within that SDK framework to take advantage of the inter-blockchain communication so that their blockchain application can communicate with others. And so that's essentially what this diagram is showing, that we're going to have multiple blockchains, in this case 5. Each of them is running an independent ABCI app, and all of them are going to be IBC aware, which means that they'll all be able to intercommunicate with each other. However, we want to be a little bit smarter about this, because rather than having each blockchain be a light client for every single other one, which is going to give us like a scalability of n squared, which is not very good, instead we introduce what we call the hub, the Cosmos hub. And the hub is this central blockchain. It's still a blockchain, so it's still a decentralized network, but it's kind of the bigger, more badass of all the blockchains around, because it's responsible for keeping up with all the others. So basically, every single one of these blockchains, which we call zones, will be light clients for the hub, and the hub will serve as a light client for all the zones. And that way, any zone can communicate with any other zone by communicating through the hub. And we can have, again, arbitrary application states on all of these zones, so long as they support this IBC protocol. So for instance, this is some arbitrary private chain, maybe some bank wants to make some application state that's going to connect it to Cosmos. This is Chainmint. There's a company called Chain in the US that's mostly funded by Visa that has some interesting application stuff going on, some cool cryptography and various forms of moving assets, and they have their own cryptocurrency language. So we could run that on Tendermint. We could also run Ethereum on Tendermint and Ethermint. OMC Go is this decentralized exchange project that could also run on Tendermint. And so we could have all of these independent application states on a common network that can all interoperate with one another. So if you have coins on one of these zones, you can move them through the hub to another zone. Cool, right? What's next? Right. So furthermore, we can actually bind some of these zones to existing external cryptocurrencies. For instance, Ethereum. So what we're showing here is, here we have the general Ethereum blockchain. It's a monolithic stack, no ABCI, right? And so it's running out in the wild. And what we plan to do is build a peg to the Ethereum blockchain through what we'll call a peg zone, which is just like any other zone in the Cosmos network, except it has the special property that it's pegged to Ethereum, which means you'll be able to move Ether from the Ethereum blockchain into this peg zone. And once it's in that peg zone, then it can move freely throughout the rest of the Cosmos network, right? So the way this works, again, is the same kind of technology as this light client stuff. Basically, the Ether will get locked up in a contract on Ethereum. On the peg zone side, the validators will verify that it's locked up there. They'll create Ether out of thin air using a proof that it exists on Ethereum. And there'll now be this peg Ether existing on the zone that will be free to move around just like any other cryptocurrency in the Cosmos network. And so using the same thing, the same approach, we can peg to other existing cryptocurrencies like Bitcoin and Zcash and so on, though we are personally only taking on the responsibility of pegging to Ethereum, and we're hoping other members of the community will take care of pegging to Bitcoin and the others. But through this mechanism, we'll be able to admit these external cryptocurrencies into the Cosmos network to interoperate with each other, ultimately, and with other cryptocurrencies within the network. Yeah.
How do you group the different blockchains? So let's say you have down here left like the private chain, and it's decentralized, so it's different chains on different nodes, or different nodes on different servers. So how do you group them? Or like you group them first and then you talk via IPC to the Cosmos hub, or do they each talk to the hub and then again to each other?
No, so you can think of them all as independent blockchains running as like a blockchain network, like you're used to, but they're aware of each other. So part of the application state on this blockchain is to keep track of the state of the hub. And same for the others. And the hub keeps track of the state of all of them. So what's not pictured here is the relay mechanism that actually enables IBC to happen. So someone has to actually be broadcasting the proofs of the latest state of the hub to the zone and vice versa. And only by doing that can these blockchains actually communicate. It's not like we plug, a TCP or a Ethernet cable into the two blockchains and have them talk to each other, right? There has to be something that can actually facilitate this communication. Okay. So the goal here is an internet of blockchains that supports scalability, diversity, security, sovereignty, and privacy. So, the really nice thing about this approach is we can experiment with many different kinds of cryptographic primitives, with different kinds of virtual machines, with different kinds of cryptocurrency designs, and so on, voting systems, social theory, governance mechanisms, whatever, all on a common interoperable network, so that you don't have to go through a centralized exchange to get access to these new networks, right? You can just launch them on the Cosmos Hub, on the Cosmos network, and then move coins into them. And so this is a really exciting way to battle test new kinds of cryptographic primitives and virtual machines and whatever, all within one system. So let's talk about scalability. There are two kind of generic forms of scalability. There's vertical scalability and horizontal scalability. Vertical scalability is just the idea of using a larger computer, essentially, or a larger database, right? You need to scale, so you add more hard drives to your computer, or you use a bigger computer with more CPUs, right? And that's kind of been the traditional approach to scaling, before the last few years. More recently, people have been looking at scaling out horizontally, which means you use not just bigger computers, you use more computers. And to do that, you have to have some kind of synchronization algorithm that's gonna keep them in sync. Otherwise, the whole thing will fall apart, and you won't actually get the scalability you wanted. So, in blockchain land, we can get vertical scalability a few ways. We can use proof of stake, which allows us to get higher throughput because we have faster commit times. We can use bigger machines because we can just design the thing so that it's not supposed to run on a laptop. That's okay. And we can use certain kinds of cryptographic primitives that allow us to actually process more in a smaller amount of time. These are things like recursive ZK snarks, and potentially other forms of cryptography, like there's this Mimblewimble project. How many of you have heard of Mimblewimble? Cool, a few of you. So Mimblewimble is like this insane idea that actually allows you to compress the entire blockchain into one block, and just forget about the whole history. It's kind of totally magic. Basically the story is, I just told the story earlier today, but most of you weren't there, was this guy showed up on the Bitcoin Wizards IRC channel, which is like the main channel where the Bitcoin developers hang out, and he just dropped a link to this PDF and disappeared. And the PDF was the title was Mimblewimble. The author was an anagram of Lord Voldemort, so people figured that out pretty quickly. And then the text was this just unbelievable description of how to use some clever cryptography, like ring signatures and stuff, to compress most of the Bitcoin blockchain. And so what's happened since then is that a lead developer has shown up. He may or may not have been the guy that dropped the paper in the first place. And so they're developing this thing, and they have a whole community of developers, all of who are using aliases from Harry Potter. So if you look at their GitHub repository, it's just a whole bunch of commits from Harry Potter characters. It's pretty amazing. So anyways, you can use cool cryptography to achieve vertical scaling. On the horizontal side of things, you basically have to shard it. You have to use many independent blockchains that are all going to be able to communicate with each other. And sharding, or this horizontal scaling, has become really popular in the database industry recently as people are scaling to many terabytes of information. You can't do that all on one computer, so there are a number of solutions, but none of them actually work in a Byzantine fault-tolerant scenario. So the blockchain community is really at the forefront of this kind of engineering, Byzantine fault tolerance in a scalable manner, and a lot of people are working on it from a lot of different directions, and us included. So if we look at vertical scalability first, we were talking about just Tendermint's raw throughput power. This is a graph that I produced in my thesis about 1.5 years ago, so things have changed. But basically what this is showing is the transaction throughput versus the block size. And so this throughput is in transactions per second, and each curve is a different number of validators. So we basically go from 2 validators in blue to 64 validators in yellow, and these are on nodes spread out across the world. So this is, that yellow line is 64 validators distributed across 7 data centers on 5 continents. and they're processing 4,000 transactions per second, which is about more or less as good as it gets for distributed systems of that size. We've done some tests more recently with 100 validators, or more than 100, I think 128, and you know the throughput goes down a little bit, but we're still in the thousands of transactions per second league. So we're still doing a lot of research on how to improve this, how to continue to make it faster and more efficient, and there's all kinds of optimizations we can still do that we haven't done yet, so we're hoping this will get a lot better. As for horizontal scalability, so this is the question of how are we going to split up the logic across these many different chains, right? And one very reasonable approach is to use application-based sharding, which is to say that different applications, will go on different blockchains, right? And typically, most of an application's logic is internal, and occasionally it has to communicate with some other application or some other contract, say. So on the Ethereum network, many contracts, they only really care about themselves and their own internal storage. Maybe there's a few other contracts they talk to quite regularly, and then there's others that they talk to on a much less regular basis. So if you wanna shard that, if you want to get horizontal scalability out of that, you group the contracts together into the ones that talk to each other the most. You put those on one blockchain, you put others on other blockchains, and that way you get that scalability that all of these things can run in parallel, which is unlike how Ethereum works now. They're all totally ordered with respect to each other. So all these things can run in parallel, and then when they need to communicate across blockchains, they still can, but it'll be a little slower and a little more expensive. So that's the trade-off. But this has the advantage that you really only have to be a full node for the application that you care about. So if you only care about one application and not the rest of the dumb smart contracts running on Ethereum, you only have to run that software, not all of it, right? So of course the problem right now with Ethereum is that it's incredibly unscalable, and like a single ICO can clog the network for hours because all of those transactions are getting processed and all the other transactions are kind of in queue waiting. So if we can split that up so that an ICO, some newfangled ICO by whoever that's going to raise $50 million can run on its own independent blockchain, then we're not going to clog the whole network, right? Because it doesn't have to communicate with any of the other contracts or the other applications. It's relatively isolated, so we can get that significant scalability that way. Diversity. So this is what I was talking about earlier, that we can have a whole diversity of different kinds of applications using different cryptographic primitives, virtual machines, and so on. So we're building this SDK. It's going to be in Golang for now, but we'll hope to have implementations in other languages later that will allow quite a diversity of different kinds of applications, different ways of putting together a cryptocurrency, different parameters for the staking or for the proof of stake, for the number of assets you can have, how those assets interact with each other, for the governance modules, and so on. So one of the really nice things about this is that the independent blockchains can have their own independent governance mechanisms that determine how they get upgraded and how they evolve without having to refer to all the others. Of course, there will need to be some coordination because some things about the application state matter to the other blockchains, but if we can define a minimal interface for that, then there's a significant amount of flexibility. And so that's really what we're working towards. So as I mentioned earlier, we have implementations for the ABCI in many different languages. Haskell should be up there as well, and I think many more are coming soon as people tune in and want to implement for their favorite language. And so hopefully eventually we'll also be building the SDK in many languages as well, but there's already efforts to build frameworks similar to our SDK in Python and JavaScript. So there's one by one of our team members called Lotion, because the goal of Lotion is to make blockchain development nice and smooth. And that's a framework in JavaScript that you can check out. It's pretty easy to use. Maybe a little bit easier than the SDK in Go. So of course, one of our primary goals early on, because we're huge Ethereum fans, at least the concept of Ethereum, maybe not the particular implementation of it right now, is to help scale the Ethereum network. So to provide some kind of first order level of scalability so that Ether can move from Ethereum into the Cosmos network, and we can have many independent parallel Ethereum blockchains as part of the Cosmos network running on Tendermint, so we get that vertical scalability, having many of them so we get the horizontal scalability to start to take some of the load off the Ethereum network so that we can be a little more confident as more applications and more use cases and more users start using that network. So this is a really interesting point. having application-specific blockchains. So the Turing completeness of the Ethereum virtual machine is really great for prototyping, right? It's a really nice environment because you have this general purpose language, then you can write this little smart contract that does what you need. But because it's Turing complete, there's a huge attack surface that you have to think about. And it's a lot harder to write a secure application in that kind of environment, right? Whereas most dApps that you want to actually build don't really need to be on a Turing complete chain. They only need a subset of the available functionality for their actual application. And so the Turing completeness of the virtual machine and its like incredible statefulness has led to a number of issues in the Ethereum blockchain. Things are hard to analyze. Certain attacks have become possible that have cost many millions of dollars, etc. So what we're proposing is that you can build your application from scratch in a normal programming language, but design it so that it doesn't provide a Turing complete virtual machine, because in general you don't need that. It provides just the logic that you need with, from a real programming language, not within this contrived virtual machine. So of course the language you're going to use is going to be Turing complete itself, because all programming languages really are, but you have a lot more control and a lot more guarantees when you're using like an advanced, well-supported programming language than you do with something like Solidity in the Ethereum virtual machine, which is a lot less mature and much, much easier to shoot yourself in the foot with. And of course, with the Ethereum virtual machine, when you have a contract and it's communicating with another contract, you have no idea what that other contract can do. It has an infinite number of possibilities. Whereas if you can build the complete application state yourself, you know all the possible execution trajectories, and you have complete control over that. So it's a much lower attack surface and a customized application build, which I think is going to be, and many people have expressed, is a lot more suited to their use cases than these clumsy prototypes in the Ethereum virtual machine. That said, there's still flexibility that can be provided to these kinds of applications, to these blockchains, through governance mechanisms. And so one of the other things we're really excited about is this experimentation in governance and in kind of social value theory and individual preferences being expressed collectively. There hasn't really been that much experimentation on a large scale with alternative governance mechanisms besides what we already have in our nation states, right? So this is an opportunity to really experiment with new governance methods and new combinations of economics and governments to see what kinds of things work in what kind of circumstances. And it's all a big experiment. We don't know how these things are going to shape out or what's going to turn out to be the best form of governance. Maybe we'll end up with things that look a lot like what we have in our current nation states and municipalities, but who knows? There's a lot to discover here. So I think these are things I already said. I should have anticipated that Sunny was going to spell them out. What was on the last slide? Yeah, that was the motivation. These are the advantages. So as we said, having an application-specific chain without that Turing completeness gives you a much reduced attack surface. It also, this is an important one, you get huge efficiency gains, because if you're operating within a virtual machine, there's a massive efficiency loss. Like the Ethereum virtual machine is very, very slow because it has a ton of overhead to actually boot this thing and manage the gas counting, and it's got a really weird stack, and so everything is like big number arithmetic, so it's really slow. So by doing it, by using a real programming language under the hood, you can get much, much greater efficiency to use whatever logic you want, whatever cryptographic primitives you want. Like if you want to use a new cryptographic primitive in Ethereum, either you have to lobby for a hard fork, or you have to implement the thing in the Ethereum virtual machine, which will be so expensive you won't actually be able to run it. Like literally too expensive to compute. So obviously if you want to do that, you need to use a real programming language. So that's a huge advantage. And of course you can fine tune it and optimize it specifically for your needs, take advantage of all kinds of traditional optimizations and software engineering tricks to build the application that's right for you. So like we've already talked about, one of the core features of Cosmos is this interoperability element, so that blockchains can actually talk to each other as kind of this two-way on-chain like client protocol, like we've discussed. You could think of it like a TCP for blockchains. It's a way for two blockchains to communicate and get acknowledgments that packets were received, and thereby move coins and ultimately data across themselves. So this is an image pulled from Blockstream, Blockstream is the company that initially came up with the idea of sidechains, which is basically using Bitcoin SPV proofs coded into a blockchain application itself to allow pegs between two different blockchains. So the Cosmos network is based on the same principles. We've just generalized it into a proof of stake context, so it's much more efficient. And we have this kind of hub and spoke model that I was showing you earlier, so that the zones are actually aware that there's other zones, and we have a kind of more integrated economic system. And furthermore, you should understand that there's a technology out there called atomic swaps, which allows you to actually swap coins across two different blockchains. It's super cool, but it has these drawbacks, which are that both parties have to be online, and there's this weird timing element that you have to provide a large time window for one party to challenge the other, and because you basically use this like little game theory mechanism to make it possible to work. So what Cosmos is offering is very different than that. It's not a swap, it's a one-way token transfer, so that you can move a token from one chain to another in a single direction without anything coming back the other way, or without having to have any counterparty. All you're relying on is the validators who are running the consensus algorithm. So that is immensely powerful and something we haven't really seen out there other than in the proposed Bitcoin sidechains, which are still in alpha or beta stage. Finally, I don't know what's coming next. Next is this issue of sovereignty, which I think we've talked about a little bit already, and like Ethereum and Ethereum Classic split because of this fundamental divide between the community. We want to be able to support those distinctions, right? We don't want to group contentious, we don't want to force contentious groups to be united under a single banner. That's the whole point of say, the first talk I gave, that these communities should be able to split and should be able to preserve their own sovereignty and yet still be interoperable. We don't want everyone to be siloed off, but we do want them to have some kind of sovereignty. So the goal is that sovereign independence and yet still be interoperable, still be able to work together despite their differences. And so that's kind of one of the key elements of the design of Cosmos, is that we can support that. Now, there are consequences of that. There are trade-offs from a security perspective, where because we don't have global control over what everyone is doing, there are failure modes that you have to be aware of, where arbitrary things can happen on an individual zone that you can't necessarily protect yourself against from another zone. And so if you have some funds on a zone and the validators, these independent sovereign validators on that zone, decide to steal your money, that's a risk you're taking. Of course, that's also a risk you're taking on the Ethereum network, where the miners can do the same thing. In fact, they did that to the DAO thief about 1.5 years ago. They stole the money back from him illegally. Arguably what he did was totally within the laws of the Ethereum network, and the community decided, no, screw that guy, we're going to steal the money back. That was probably the right decision. I'm pretty happy Ethereum forked. I think it was a really strong signal to them. No, seriously. Why are you laughing? Yeah, I got my money back too. So I threw money at the DAO with like 2 hours left. I was holding back the whole time. I was like, this is dumb, this is dumb, this is dumb, this is dumb. And there's 2 hours left in the sale, and they had already raised like 200 million. And I was like, oh, fuck this, I don't want to miss out. So I threw like a few ether at it, whatever. And then like a month later or whatever it was, the whole thing blows up.
And then we have Ethereum Classic now.
Yeah, we have Ethereum Classic now, so it's good. No, but it signaled that there really was a divide in the community over how this blockchain should be governed. And some felt the code is law and there's no such thing as theft. There's only just following the rules. And others felt, well, actually theft is a real thing and we're still human and we care about like human culture and politics and intention. And despite the marketing materials pushed by the DAO, which exerted that the code was law, and if there's a difference between the documentation and the code was right, we really didn't feel that way. We really felt the documentation was what we should be following, and that the intention was that someone would not be able to steal $50 million worth of all our money. So it's pretty amazing that the Ethereum community was able to do that, execute that hard fork, and we want to preserve that kind of possibility for independent zones within Cosmos. Yep. Yep.
Oh no.
All right.
Go back.
Go back?
Yeah, merge miner.
Yeah. No, go forward.
Okay, thanks. I hope Sunny doesn't see this. Implications of the Internet of Blockchains. So, I think we've talked at length about a lot of this stuff, so I'm probably just going to be repeating myself in the interest of covering Sunny's slides completely. But the essential idea is that we can have all of these application states on a single network so that you can use a token between all of them without having to convert through an exchange. And of course, we all know the problems with these exchanges is that they're highly precarious, they're highly fragile, they're centralized, they're single points of failure, they're constantly getting hacked. Many of them aren't publishing proofs of reserve, so we don't really know what's going on. So within a system like this, you can avoid that. And that's a hugely powerful potential opportunity, especially for people who have lost money on exchange hacks.
What is the little circle one with the 3 circles? Is that
That's Ripple, but forget about Ripple. Ripple sucks. They just added Ben Lawsky to their board. Ben Lawsky is the guy who's trying to destroy Bitcoin in New York, and apparently Ripple thinks he's great, I guess. Bitcoin's competition for Ripple.
Wow.
Do I have changes to state?
Skip this one?
Yes, good.
Skip this one? Okay. I tried to ask Sunny what he meant by this slide, but he didn't get back to me, so I'll just show it. Same. Bunch of stuff. Bitcoin is king. So me and Sunny actually share a philosophy that very few other people at Tendermint, perhaps no one else at Tendermint feels, which is that Bitcoin is king. So, as much as Jay started the Tendermint project in an effort to overcome Bitcoin's fundamental flaws and may actually, I don't want to put words in his mouth, but I have the impression that he feels Bitcoin is wasteful and we should probably get rid of it. I don't feel that way, and Sunny doesn't feel that way because Sunny's a smart man. And so both of us feel that there ought to be one and only one large-scale proof-of-work blockchain that is kind of the anchor for everything else. And I'm totally fine if that thing uses more energy than every other country on the planet. I don't actually think that's a problem. I think focusing on that is a real red herring compared to all the other issues we have to solve. So go Bitcoin, go Sunny, and I hope to anchor a huge internet of blockchains into the thermodynamic immutability that is bestowed upon us by the Bitcoin blockchain. Yeah, there's more. I mean, we've talked about this stuff. We want applications to be able to talk to each other. So far, we're focusing on token transfers because that's the easy thing to do. Down the road, we're going to focus on data transfer as well. There are ways to do it, but it's hard to provide the same kinds of security guarantees. So there's a lot of interesting work there. If that's something that interests you, you should reach out and contribute your ideas and research efforts. This is also a huge selling point that's going to be really important in the future is this interoperability between the so-called private and public networks. So there's going to be lots of enterprises and businesses and organizations that want to run private blockchains that aren't fully accessible to the world, but they're still going to want to interoperate with these larger public blockchains. And so what we're hoping to build in ways that these primitives are useful in a general purpose way, that IBC can be used across different kinds of blockchains, between private, public, doesn't matter. You have to satisfy a small number of constraints to be able to use these protocols. And that's kind of our philosophy more generally, is to build general purpose building blocks that can be used in many different circumstances and composed according to the needs of the user, rather than go out with a monolithic stack and say, this is the way it has to be. And so, we're using these pieces to stitch together the Cosmos network. We're doing the best we can to ensure that it will be successful. But at the end of the day, we can't really know what the right way to build something like this is. And so at the very least, we hope that the tools we build will be useful in a general purpose way if the network we put up ultimately isn't. But we're relatively confident that the decisions we're making are reasonable enough to guarantee the success of the network. Another huge, so I guess he's just showing that there's lots of cryptocurrencies out there and they all have different prices.
You're supposed to say which position ERC20 tokens are on this graph, and then forward until you find one.
Oh, cool, great.
They're low.
So
They're low.
the ERC. So these are all the native coins of independent blockchains. It's kind of amazing. None of these blockchains talk to each other. They're all just siloed off independently. And the only way to move between them is a centralized exchange, right? This is the problem we're trying to address. So this is why we're building Cosmos, and we also have a design for a decentralized exchange that will live inside Cosmos that kind of gives you the best of both worlds. You can have centralized order matching for speed and efficiency and privacy, but you have decentralized custody. So the exchanges are left with the thing they do best, which is matching on the order book, and they don't have the liability of being a custodian of everyone's funds. So it's a really nice design that kind of combines the best of both worlds. So as we move through, we're looking for an ERC20 token. I don't see one. I don't see. Oh, Augur.
Augur.
There you go.
There you go. And
28.
there you go.
Cool. So Ether Delta is an on-chain exchange. There are all kinds of problems with that with respect to front running and efficiency and so on. But there are a few other projects like Kyber and OpenSea Go that are working on more efficient decentralized exchanges that take advantage of more off-chain components. And so we're working with both of them on these designs and collaborating to actually make this a reality. Finally, he threw up a slide here on geographic sharding, which is kind of the idea I was talking about earlier in the first talk about actually breaking down and orienting the scalability of these larger networks in geographic regions so that they're focused in these local communities where most of your commerce actually happens. Arguably, that's the right approach to scalability, the right approach to governance. It solves a lot of problems with respect to accountability and may help make much more robust and sustainable local communities. So again, if this is something you're interested in, I would love to talk more about it. I've basically gotten to this whole blockchain space because it clicked in 2013 that here was a potential to roll out technologies that enabled local currencies and the rewarding of valuable behavior within a given community. So Bitcoin provides rewards to valuable behavior within the Bitcoin community, which is effectively offering your security to the network. But there's no reason we can't roll out local currencies that are issued to people who contribute valuable behaviors to their community, whether that's growing food or distributing food or looking after the elders or teaching kids or giving workshops about the future of cryptocurrency at Notman House and so on. So yeah, that's that. Thank you so much.
I arrived late, so you might have answered this question already, but what's the patents and licensing scenario around that technology? Are there patents there? Is it licensed? How does it go?
It's all open source. Most of the tech is licensed Apache, which means that enterprises can take it and use it in a closed source way if they want. So a good chunk of the Ethereum stack is actually GPL, which means it's one of these viral licenses that you can't close source. So that was part of the reason. Actually, it was one of the benefits of implementing Ethereum from scratch on top of Tendermint is that we could license it Apache and it could be accepted into Hyperledger. But in general, this technology is not patented. There have been cryptographic primitives that were patented, but those patents have expired. For instance, Schnorr signatures, which are becoming really popular. So that's going to allow a whole bunch of vertical scalability itself. That's something I didn't talk about. But yeah, in general, it's pretty patent-free and it's all open source. If you talk to a blockchain company that's not open source or that claims they have a proprietary solution, they're a scam, and you shouldn't listen to them. Sorry.
Can you explain a little bit more about how the token transfer works?
Yeah. So the IBC mechanism is this light client protocol, right? And so what the hub and spoke model allows is for the hub to enforce invariance over the token supply across the zones, which is to say the zones effectively have an account balance on the hub. So if I have some token, call it token A, and I send a bunch of them to the zone, what the IBC protocol allows us to prove that so if I have token A on the hub and I want to send it to the zone, right? So I can send a transaction on the hub that says I'm sending token A to the account of this zone, right? Then someone can publish proof of that to the zone. They can say, hey, look, here's a proof that on the hub, these tokens were transferred into your account. So that effectively will create those tokens on the zone so that they can then move freely around the zone. And then the same thing can happen the other way. So once you want to send those tokens back from the zone to the hub, you send them to an account on the zone that is effectively the account of the hub on the zone. And then someone can publish a proof that that happened to the hub and can say, hey hub, look at this. Here's proof that these tokens are locked up on the zone destined for you. So you can now unlock them on the hub and they can move around on the hub. So that can happen for any number of tokens, for any number of zones. But the hub can enforce this invariant that says a zone can only transfer out as many tokens as it has. And that way zones can't just create tokens out of thin air. But because we want zones to be able to be the source of new tokens, we get around that a little bit. We say some zones will be the source of a new token, and they'll have some emission rate, which means the hub will accept the creation of new tokens at some rate by that zone, so that the tokens can be emitted according to whatever the rules are of that zone and can be transferred out of the zone onto the hub. And it's basically up to the other zones in the community to accept that emission rate and to trust that it's happening according to the rules of the zone.
Is there a notion of an intermediate token, like stellar lumens, for example,
No.
that are, no, there isn't?
There is a native token called Atoms.
There is a native.
But it's a multi-asset cryptocurrency, the hub. So it supports natively many different kinds of tokens, all using the same mechanism. That said, on the hub, there's only one kind of token that's accepted for the staking. So the point of the Atom was that it would be the token that is staked in these security deposits that would incentivize the validators to actually do the validation, and that they'd be paid out rewards in. But there will be other tokens that you can pay your fees in, and on some of the zones down the road, you'll be able to stake independently in other tokens.
And it has a certain inflation rate.
That's right.
Yeah. And that's constant. It doesn't. I mean,
It's actually dynamic, but it does have limits. And the reason for that is because we want to incentivize a certain number of validators. So if there aren't enough, a certain number of stake to be bonded. So if there isn't enough, the point of the Atoms is for pretty much all of them to be bonded. But the problem if all of them are bonded is that then there's no liquidity in the market. So it's hard to establish what the price is. And then you can't really evaluate what the economic security of that thing is, right? So you need a certain amount to remain liquid and unbonded. But we want a sufficient amount to be staked. So what we do is we have a high inflation rate to disincentivize people from holding the Atoms liquid, to encourage them to actually stake them. And so if the amount staked is too low, the inflation rate will go up to some point. That's right. So if you're going to hold Atoms, the primary reason to hold Atoms is to stake them to participate in the security of the network. If you're not interested in participating in the security of the network, you shouldn't be holding Atoms. They're not meant to buy your coffee or to buy anything else. They're not really meant as a store of value. They're meant fundamentally, they were designed to be this staking token. Yeah.
How do you differentiate inter-blockchain protocol to inter-ledger protocol, which is proposed by...
by Ripple. Yeah. The interledger protocol is stateless. So it's just really like a messaging format for communicating information between chains, and typically it draws on payment channel or state channel mechanisms. So it does the kind of things that it's like a way of formalizing atomic swaps. So atomic swaps are what I was talking about earlier, where you have to have people available on both sides, and they swap across the two chains, right? So it's stateless, and it uses these kinds of hash-locked and time-locked payment channel mechanisms to actually facilitate the movement of data. The Cosmos IBC is different from that because it actually maintains authoritative state. The validators themselves are responsible for holding onto the state, and the IBC allows you to publish proofs that there is an intention from one set of validators to move coins or data to another set or to another consensus set. And so you can have this kind of one-way authoritative flow of information that is stateful compared to this two-way, non-authoritative, non-stateful flow that requires both parties to be online. Yeah. So I think we might be able to use some of the formats and some of the protocol from the interledger, but we haven't looked too closely at it. Anything else? Yeah.
How would your ideal local community currency generate coins using consensus?
So I couldn't possibly decide that because in my ideal way, the communities will decide what their ideal way is. So, if I were to run my own community, I guess I haven't thought that through fully. Right now, I'm kind of obsessed with food security. So the most important thing to me is to fix the incentives around farming. Right now, our farmers are all bankrupt and under huge amounts of stress, even though they're like the bedrock of society, and people often forget that. So if I was going to start a local currency, I would probably set up systems to issue the coins to the farmers who are producing like local organic food, and I would start from there.
How will you govern slashing if validators act in a Byzantine fashion?
So the slashing is automatic for now on the Cosmos network. Basically the way it works is if you find that a validator was explicitly Byzantine in the sense that they double signed, like they try to fork the blockchain or double spend, anyone can publish evidence of that, non-refutable evidence of that. And once that evidence is received, the validator will just be slashed automatically. Now in the early days, because the software is, relatively new and untested in the wild, we'll probably reduce the total amount of slashing, but we're still working out all the specific details, and hopefully we'll have a paper up in the next couple of weeks that'll walk through kind of all the specifics about the parameters and so on.
So do you punish them when they go offline as well?
We don't slash them, or at least the plan isn't to slash them, but it is to reduce their rewards.
Right.
Right. So they won't get rewards if they're offline for too long, and eventually they'll be automatically unbonded. But we're not gonna. I don't think we'll be slashing them.
So is there an architecture that you propose for?
Sorry, can you say that again?
So regarding the geographical placement of validators, do you have anything in mind?
Not quite. We are encouraging a pretty decentralized set, and we do have interested validators from all over the world right now, and we're continuing to nurture that. So there's people all over Europe, there's people all over North America, in Canada, in the US, in China, in South Korea, in Southeast Asia actually also, and those are the jurisdictions I'm aware of right now, but hopefully there will be much more, and we're certainly trying to encourage a more widespread distribution, but it's hard to actually enforce that. Yeah. Yeah.
Talking about local cryptocurrency, I'm also a believer in that, and I created a prototype. It's called the Fit coin, and Fitness coin, and you could mine some Fit coin by cycling around the city, and would like to get your feedback on it. So.
Cool. That's a great idea. I just am concerned about, in general, about the gameability of these systems. So how easy it is to create coins by like spinning a wheel in place with a motor. So if you can protect against that, then I think it's brilliant. Yeah. Yeah.
I'm very impressed, but it's very theoretical, at least in my mind. So suppose just trying to make it more concrete. So suppose I build games, okay, and I want to have my own blockchain for that, those transactions for my games to be efficient, and I also want to tie in Ethereum, for example, because I want some real value to be in the game, whatever the game may be. So how do I use Tendermint? Like, if I run my own blockchain, one of the questions I have is, who's validating it? Is it on your blockchain, or I have to set up and find my own validators?
Yeah.
Can you make it just a bit more concrete?
Sure. So both options are going to be possible. In the early stages, it'll always be the same validator set, just for the sake of simplicity. So what you'd be able to do is you build your game, you build it on top of you build it as an ABCI application, so that it'll run on top of Tendermint, which means it'll run in a distributed way, kind of automatically. So you build the state machine in whatever programming language you want, and then you satisfy the ABCI interface so that transactions come in, you deserialize them, pass them on to your state machine, process it, returns results. So that'll run on Tendermint. But you're also going to want to support, you're going to need to support the IBC protocol to allow the inter-blockchain communication. So if you program it in Go and use our SDK, that'll be provided for you. If you want to build it in another language, you'll have to either wait or implement the IBC component yourself. As far as which validators are going to run it, initially it'll just be the Cosmos validator, so you'll be able to pay to say, hey, I'm launching a blockchain, will you guys run this? And there will be some fee-based mechanism for getting the validators to actually run this new blockchain in parallel. And then you'll be able to determine what kinds of tokens this chain is allowed to accept. So when you initialize the thing and set it up on the network, you'll say, okay, it's accepting these tokens, right? And that'll be able to change over time. And so you can specify that it'll accept Ether once there's actually a bridge to Ethereum. So then Ether can flow from Ethereum into the Cosmos network, and then into your zone, it can be used to pay for the services or whatever the game aspects are on your zone. Does that make sense?
Yes. If this state machine is in, let's say, Python, how can people validate the code and what it's doing? Who's running that? Is it like I have my own CPU running that?
No, the validators will actually run it. So
they'll run the Python code?
Yeah. But they have to elect to do that. They're not just going to run everything anyone pushes up, right? Because they're going to have to select basically which code they're willing to run. So initially, there's going to be only a small number of zones because of this bottleneck that all the validators are going to be running everything, right? There's still some scalability there because they can run it on different machines. Down the road, you'll be able to set up your own validator set, your own network of validators, incentivized however you want to facilitate that.
And how are they going to determine how much they charge me to do that? Running my Python code?
Yeah, that'll be up to the market.
Okay. So I propose the code, they look at it.
Right.
What's the cost comparison to Ethereum for running applications?
We don't know yet. We haven't launched.
When are you launching?
Soon. 2 weeks. 2 weeks TM. Ethereum was going to launch in 2 weeks for like 6 months or something. Yeah.
Since there's some limitations to universality of your blockchain compatibility. For example, if a particular blockchain invokes multi-signature algorithm, I sense the capacity will be because and maybe the protocols. Is that correct? You're not really developing a universal recipe for communication in blockchain. You restrict it to certain to similar types of blockchain. Is that correct, or
sort of?
So elucidate that.
Yeah, sure. So basically, what the IBC protocol is it's just a general purpose light client protocol for proof of stake cryptocurrencies with Merkle trees. Okay, so you can store arbitrary data in a Merkle tree, and proof of stake cryptocurrency is a pretty general purpose thing. So the IBC, basically what it consists of is headers from blocks and signatures on those headers, and it's responsible for keeping, the way the light client works is you have to keep up with changes to the validator set. And if you're able to keep up with those changes, then you can verify the signatures on the header, and then you can verify any Merkle proof in that Merkle tree that has the root in the header, right? So whatever you can put in the Merkle tree, you can verify. So now the question is, how do you layer data and information on top of what you're sticking in the Merkle tree? And that's a very general purpose thing, and you can pretty much do anything. The challenge is what kind of guarantees you can enforce at the network level about the movement and validity of that data in a general purpose context. And that's the kicker. So initially, we're going to start with coins because the hub can enforce certain global invariants over coin movement. For instance, if Zone A only has 10 tokens, then Zone A can only ever send 10 tokens out. And if Zone A, tries to publish a proof to the hub that says, hey, we're sending 11 tokens, even though there's a valid proof from Zone A, as far as the hub is concerned, the hub knows that they only have 10 tokens. So they're going to say, no, you can't send 11 tokens. You're obviously being malicious. But in the case where Zone A is sending arbitrary data and the hub doesn't know anything about the semantic kind of underpinnings of that data, the hub can't enforce anything intelligent about the structure of that data and what's allowed. So in general, for the hub to enforce invariance is very difficult, and you need a more general purpose mechanism that kind of audits the actual execution of the state machine on the zone. That's a project for later. There are a number of projects in the space that are working on this problem. For instance, TrueBit. And basically, this is this general purpose problem of how to audit and how to verify the execution of a state machine without running the whole state machine yourself. Right? This is the challenge. And there are some very clever cryptographic and game theoretic ways to do that. So TrueBit is basically a game theoretic way to do that uses basically a Merkle tree of the execution trace, and it audits that. But it's like a challenge response protocol. So that's one way to try to solve this problem, and basically say, okay, I'll accept this thing for your general purpose state, even though I don't understand it, but maybe someone will challenge it later, and then I have to arbitrate that challenge and kind of figure out who is correct here, right? And that's something we can do, and basically we're offloading that onto TrueBit for now, who's working on doing that on the Ethereum network, and hopefully we'll be able to work together to expand the security of Cosmos. Another approach is to use ZK snarks. So ZK snarks are a recent development in zero-knowledge cryptography, which allows you to prove, and this is magical, so I'm going to say it slowly. It allows you to prove you executed a known program on an unknown input without revealing the input. So, once again, you can produce a proof that you executed a program on a secret input and got a given output without ever revealing the input, which will exactly solve this problem. Because then I can get proof then all the hub has to know is what that program is. And then the zone can produce proof that they ran the program correctly. And then the hub doesn't even have to trust them. They just verify the proof, right? So the ZK Snark technology is going to completely, it's a total game changer for blockchain scalability. It is going to open up a huge number of avenues. The problem with it is right now it's relatively inefficient, so it still takes a few minutes to actually produce these proofs. It only takes milliseconds to verify, so they're succinct and very quick to verify, but it's still expensive to produce. The other problem is that they're not going to be quantum proof. So there is a new development now called ZK Starks, so with a T instead of an N, that is quantum proof, but is even less efficient from a space perspective. And so from a storage perspective, I mean. So there's a lot of active research. This is incredibly challenging technical material. It's about as technical and complicated as cryptography gets. I've never seen anything quite as bad. So it's really going to be a challenge to raise a generation of cryptographers that can actually understand this stuff and innovate on it. But I'm quite confident that with developments in the space of zero-knowledge proofs and in like game theoretic challenge mechanisms combined, we will be able to address this problem. So you're right that right off the bat, it's very difficult and we don't have a good solution, which is why we're mostly focused on token transfers where we can enforce these global invariants. But down the road, when the zero-knowledge proofs become more efficient and potentially these game theoretic mechanisms become more efficient, we're off to the races. But good question.
So I can see the principle of the exchange for tokens and all that for the Cosmos. You have other real-world examples of what this could be useful.
Yeah, I mean, like we kind of fall back on anything Ethereum is useful for, right? Because basically we're going to provide a scalability ramp for Ethereum. So you'll be able to run Ethereum applications on Cosmos just in a more scalable manner. So anything you think Ethereum is useful for, Cosmos will be useful for, but more because it'll be more scalable, at least initially, and because you have more customizable possibilities as far as the application state goes. Yeah. Anything else? Yes.
I'm wondering, is the hub limited to the transaction time of when other platforms being used, like Ethereum is like, 17 seconds transaction time? Like, is there any way that there could be like a part of it that allows for higher transaction time?
Yeah, so the hub will have much higher throughput. We're gunning for about 1,000 transactions per second. We can do that now. Sorry?
That's going to be like the new average across, even if you're running like the Ethereum.
Yeah. Yeah. So the hub won't run. The hub doesn't support the Ethereum application state itself. The hub is a much simpler application state that is going to be relatively highly optimized for a minimal amount of computation, so that we can support high throughput. The actual Ethereum computations will happen off on a zone. So you'll have some Ethereum zone, but it's going to be running on Tendermint instead of Ethereum's proof of work, which means right off the bat it'll be able to support much higher throughput on the order of hundreds of transactions per second. The limit there is the Ethereum virtual machine is quite slow. So when we benchmark Ethermint, which is the Ethereum virtual machine on Tendermint, we get around 100, few hundred transactions per second, depending on what kind of contract we're benchmarking. Yeah, thank you. What's up?
Are you familiar with Holochain?
No.
Never mind that.
Should I be?
Yes.
Cool. I'll check it out. Hit me.
What kind of network partitioning? What kind of network partitioning would you have to see between the validators before you can no longer, before the consensus algorithm can no longer guarantee that things are guaranteed, like instant validation, things like that?
Yeah, awesome question. So, as I said earlier, the Tendermint is safe in an asynchronous network. So it means you can partition it however the hell you want, and you'll never have inconsistency, unless you have too many Byzantine validators. So the assumption that Tendermint makes is that less than 1/3 of the validators are malicious. So assuming that less than 1/3 of the validators are malicious, Tendermint will never have any inconsistency, right? And we can prove that formally, and we've done some rigorous testing to show that Tendermint actually satisfies that empirically. So there's a tool called Jepsen, which is kind of like the industry standard, like distributed systems testing kit that most databases fail. So whenever he runs, people hire this guy Kyle to run the Jepsen tests against their particular database, and in many instances, very quickly he's able to show that it violates guarantees. Tendermint had some minor issues that were kind of just like unrelated small bugs that we quickly squashed, but he ran very extensive tests against Tendermint. I think he said they were the most complicated tests he's ever run because he's never tested a Byzantine fault tolerant system before, and we did lots of validator set changing. and he could not get Tendermint to violate his guarantees. So he wrote up a report. You can read it. Google Jefferson Tendermint. It's funny, if you look at like Reddit comments or whatever, everyone is surprised to see something actually not fail the Jefferson test.
So I'm aware of Jefferson. That's pretty impressive.
Yeah, thanks. So, so that's on the safety side. On the liveness side, we require at least 2/3 to be online, sorry, more than 2/3 to be available and communicating to make progress. So if you have a partition such that you don't have more than 2/3 within one partition, then we're gonna halt. And we won't continue to make progress until that partition heals. But Tendermint is somewhat optimized so that relatively quickly after the partition heals, we'll start making progress again, and you won't have to wait too long. Yeah, great question. Yeah.
Can you detect if you have more than 1/3 malicious agent or less than 2/3?
Yes, you can. So Tendermint also has this accountability property, which is kind of a new property that's not really well defined or seen anywhere in the literature, and is still kind of open for debate on what it means and how to design protocols that achieve it. But the idea is that in the event that 1/3 or more of the validators are malicious and cause the network to fork, i.e. they violate the consistency properties or the safety properties, we can identify exactly which validators were responsible. And so at a social consensus level, we can look at that and we can say, okay, these are the guys that's responsible. Let's start a new network with all the same validators except for them. So that's kind of the recovery plan in the event that that assumption about 1/3 of the validators is violated.
So what you just said is this is going to ensure it doesn't fork.
Tendermint will not fork, assuming less than 1/3 of the validators are malicious. If 1/3 or more are malicious, they can fork the blockchain, but then we have this accountability property that guarantees we know exactly which validators were responsible for the fork, so that we can restart the blockchain without those validators. But doing that restart can't be done in protocol, of course, because the protocol just failed, so we have to rely on some external mechanism, external means of communication, and synchronizing, like at a social level, to figure out how to restart and when.
How does pushing updates function to applications?
That's application specific. Good question. Yeah.
Well, like without changing blockchains, like it can work.
It can work, but you have to accommodate like hard fork logic and all this kind of thing. So it will get a little bit messy. There is going to be relative flexibility in doing that. I mean, that's kind of the point of these independent zones, is that they can upgrade according to their own schedule or however they want. In the event of contentious forks, it will be complicated. So we're working on kind of specking out what that's going to look like and what people should brace for. But yeah, it'll be a little messy. Exciting. Yeah.
On the credibility of validators for inclusion or exclusion, does that mean that the mechanism will be somewhat centralized?
How do you mean?
Well, if you need to exclude somebody because he's being
Malicious.
Yeah, malicious.
Yeah. So in protocol, the way that works is anyone can publish evidence of a malicious validator. So if you detect that some validator has been malicious, you can publish evidence of that, and that evidence will get included into a block, and that validator will be slashed. So the protocol will remove him automatically, right? Now, if 1/3 or more of the validators are malicious, then they can prevent themselves from being slashed. So we have to pivot to an external social consensus mechanism. If you want to call that centralized, arguably, I guess that's okay, because we will need some kind of synchronization element. We'll have to rely on people either having synchronized clocks and saying, okay, at midnight the day after such a failure, we're going to restart the network without those validators. I mean, that can be done in a relatively decentralized way, but it won't have the same guarantees that we have when the protocol is functioning correctly. So this is a really challenging problem, and really we're going to rely on having a robust and aware and active community supporting the network to be able to recover from such a failure. I mean, if you look at what Bitcoin has to do, right, like they have the same problem. When a bug is introduced into the software and suddenly the Bitcoin network forks irrevocably, thank goodness that there's a small concentrated number of developers and like business leaders that all have each other's phone number and Skype number, so that they can immediately talk to each other, figure out what went wrong, and manipulate the entire community to fix the problem, right? So thank God for the centralization. The Bitcoin community hates when I say that.
So the application layer is communicating via ABCI over a socket. I was just wondering if you could explain the socket. This is a web socket. Is this secure? What do we have here in this socket?
Yeah, so you have a few options. It's not a WebSocket because we're not speaking HTTP. It's just it's like a standard. It's a TCP socket essentially.
TCP socket.
So you can use the network interface and have like a normal TCP socket, or you can use a Unix socket so that you use the file system.
Okay.
Typically, we anticipate that the app and the consensus engine will run on the same machine. So we don't really worry about securing the socket, like using any kind of.
It's essentially localhost.
It's localhost.
Yeah.
That's exactly right. Now, in the event that you were to run it on a separate machine, which is totally possible, the security of that socket is kind of left up to you.
Okay.
We haven't really built anything into Tendermint because we haven't seen a need to support a cross-machine socket protocol yet. Yeah.
Cool. Thank you.
Yeah. Yeah.
So you would never have a need to horizontally scale the application layer while not scaling the consensus layer?
That's a good question as well. You will, there is a need to scale at the application layer. For instance, if you can identify that certain transactions can be run in parallel, then you ought to run them in parallel. So, you know, to a certain extent, the bottleneck, you know, there's a bottleneck at the consensus, which is like you can only run so many transactions through the consensus per second, right? So, in general, like modern high-performance CPUs or like a standard kind of high-performance desktop that would run such a validator is going to have enough concurrency that it would be able to support sort of parallelizing whatever transactions it could parallelize, that you wouldn't actually need to worry about running the application itself across multiple hosts. Maybe down the road that will change, but that's certainly not a focus for right now. Keep them coming. Yeah.
I showed one slide with Golem on it. Is there some relationship with Golem? There was no mention of anything there, just showed the name.
Yeah, you know, these are so many slides, so maybe that was just an example of an application-specific chain, i.e. like Golem doesn't need a Turing complete backend. So yeah, as far as I know, we don't have any like close relationship with Golem, but that's a cool project. Yeah. What else? You all satisfied? Satiated? Time to go home? What's up?
Just curious, this project, just characterize it.
The Cosmos community?
Yeah.
Awesome.
That said, just curious.
Yeah, so. Yeah. Sure. You know, a big chunk of it comes out of the Ethereum community. Certainly, there's a lot of people that got frustrated with the Ethereum development environment and saw the opportunity to build in a real programming language, a distributed application, and that really excited them. So there's a lot of people that are just, you know, generally were interested in Ethereum, love the possibility of contracts and so on, but are also like actual real software engineers, not just like random web developers that want to decentralize everything. And so are taking like traditional software engineering approaches to building state machines that run in a distributed environment. So that's a chunk. There's also a bunch of people that are just super excited about proof of stake and see us as like, you know, kind of on the frontier of the kind of proper secure proof of stake, and there's all kinds of interesting economic questions in there, so there's a lot of people interested in that and working on that, concerned about that. There's a lot of people that are just like die-hard Ethereum folks that see this as an opportunity to scale Ethereum, and so for that reason are invested. Yeah, so I think a lot of it borrows from the Ethereum community, but there's also a big enterprise side as well, because you know Tendermint is used, I think, in a number of enterprises. We found out a few months ago that Oracle is using Tendermint, and they published a patent that mentioned Tendermint like 30 times. Yeah, how do you like that? So yeah, there's kind of a mix of those. Yeah.
Hey, how many hours have you been on your feet?
8.
This guy has more endurance than anybody in the room.
Thank all of you for coming out.
Hey,
yeah.
thanks for.
You bring up a really good point about Oracle. Is that a concern for you?
No.
They could, like, not them, but someone could out-patent to develop something that would hold the.
No. They can't patent Tendermint. It's been around for too long. They patented some dumb protocol that like they built a prototype of using Tendermint, and so Tendermint is just their like example.
But in the future, is that like patents aren't a concern for you?
Patents are a concern. I'm terrified by the state of the legal system, but there's a number of folks that are working towards like defensive patent pools and so on. I'm also not very optimistic about the ability of like the U.S. government to hold itself together for all that much longer. So I think
it's an open source fucking project. Why do you want to fucking have no idea?
Thanks, guys.
Why do you want to centralize and decentralize the idea?
An amazing talk. And beyond the amazing talk, there's also lots of amazing questions. And I urge all of you, not just to get in touch with you, but get in touch with us. We're always hiring. So if anyone working in these areas, this field, by all means, blocksense.io, give us a ring and you're worth the damn, we'll pay you.
On behalf of the whole Blocksense team and everybody at we made these garments.
Wow.
Oh yeah.
Oh my god. Oh my god.
It's pretty good. So that's a come on now.
What? Are you kidding? No. Wow. That's great. This is awesome. This is the coolest piece of clothing I've owned.
Very nice.
Oh yeah.